Hello YouTube, and welcome to what is almost definitely going to be the shortest video I do for Physics C. We're going to talk about power, I guess. So in particular, you should be able to model the power of an object when given its work or time, or able to make an equation for work. And you can do this if you can divide work by time. The stuff that the AP exam just does with power is not particularly complicated. You just have to know that it's there, and you have to not freak out when you see the word, because you're like, oh yeah, we talked about that a little. It's like there, you just divide by time. Great, good. So if something does a task quickly, it's going to take more power than if something does it slowly. And that's pretty much it. The reason that power is particularly important and a particularly useful measurement for like electrical appliances and stuff, and is that if you have someone who buys a light bulb and you want to be like, okay, well, this is the energy usage for this light bulb. The problem is that you can't tell them how much the energy the light bulb will use while it's on, because if they leave it on for 2 hours, then it will use a lot more energy than if they only leave it on for 10 seconds. And so what you can do is you can tell them the energy usage for every second that it's on. And that's what power is. And so it's this really useful concept for like modern life, even if it's not a like interesting concept for solving physics problems most of the time. So the equation is just that average power is equal to work divided by time. It's measured in watts, which have units of W. So it's annoying because the variable W doesn't go with the units W, but otherwise it's pretty straightforward. If you want to find the instantaneous power, it would be the derivative of work with respect to time, or the slope on a work time graph, or time versus work graph. So super quick example, we've got a motor lowering a 5 kilogram block down a frictionless 10 meter tall hill from rest. At the top of the hill, the block is going 5 meters per second, or sorry, bottom of the hill, that should say bottom. The block is going 5 meters per second. How much power did the motor use if the trip took 10 seconds? So we've got this situation, we've got our thing, we've got our motor lowering our block from here to here. We've got our height. Oops, I got a little overeager and just went straight to the potential energy equation. 10 meters. And we've got our velocity at the bottom of the hill is 5 meters per second. And our velocity at the top of the hill is 0. So at the top, we've just got potential, mgh. Our motor is going to do some work, pulling the object backwards with like a rope or something. And so we've got our negative work from our motor. And that'll equal the energy at the end, which is all kinetic, so 1/2 mv2. We're asked to find our power, but that's always just going to be work divided by time, and time is a given of 5 seconds. So I can just go ahead and throw some quick maths at this. If we subtract mgh, subtract mgh, and then make both sides negative, what we'll get is that our work from our motor is equal to mgh minus 1/2 mv squared. If we want power, we just have to take that work from our motor and divide it by the time. So mgh minus 1/2 mv2 squared divided by our time. So 5 times 10 times 10 minus 1/2 times 5 times 5 squared divided by 5. So 100 minus half of 25, which will give us 87.5 watts of power. That's it. Like, that's the most complicated thing you'd be asked to do with power. You might have a more complicated energy question and they drop power at the end, but like the power part of the problem is going to literally just be, I don't know, divide it by time. Or like if you have the power and you have the work, rearrange so you solve for time. It's never going to get tougher than that. that's pretty much it. It's just this little thing that we should definitely remember to talk about, even though, because it is more of an important concept than I'm giving it credit for, but it's just not a particularly hard one compared to a lot of the stuff we do. So that's it. Goodbye, YouTube. Hope you have a great night.